All right, this time I actually remember to unmute the microphone. Well, hello everybody. Monday, so we've got sort of another video for you for Math 4 here. We're still in our unit with exponents and logarithms, but we're going to start off with a little bit of something maybe kind of familiar. What's the letter of the day for Sesame Street? E. Now, unfortunately, I have some news about that though. When I say E, the lowercase e, it's not actually a letter, it's really a number instead, which might make you kind of think, well, hold on, what here? If you time traveled 5-6 years ago, told yourself E is a number, you're going to look at yourself like you're crazy. So, let's dive into this. We're going to start a little bit with, can you just write sort of a basic exponential equation and establish where this number comes from? Okay, it's a weird sort of number. It is a number that exists. We're going to spend a little bit of time today working through that and like where it comes from and why. And then tomorrow a little bit more nuance around how to actually use it. But functionally, everything you know about properties of exponents and logs is still true. Okay? So we've got basically here a situation, we've got a 300 million population, we've got sort of a growth rate. We want to know like what equation would you basically write for this, okay? That 300 million is sort of the amount that you're at with a growth rate, sort of 1% per year. Oh, that's off. Should change that guy to a 0.01, but there, nothing too crazy. I don't know where oh, my apologies. I guess that's a 0.0 or 0.8% in that case. But you see where that's coming from, right? Okay, that one's off a little bit. If we have, all right, annual rate of 5%, saying their investments, we're going to invest 50,000. Figure out how much this is going to basically be in the account after any amount of years. 50,000, our starting value, times 1.05. That 5% gets added on. I apologize for that previous one. Based on however many years you sort of just let it sit in there. If you're getting that extra 5%, great. A little bit wordier here with a situation with medicine, given a 250 milligram dose, and your body is basically sort of like taking 10% of that per hour. Understand that how much is left in the blood is not 10%. It's how much is left is 90 in this case. So we're starting with 250, and basically because we lose 10%, you keep 90. Right? 250 is my initial value. I'm losing 10%, I'm keeping 90. A 10% decrease or decay subtracts from 1, whereas a 10% increase would add on to 1. Now, all of these should feel pretty simple. Like you've seen this sort of stuff way back in Math 1. We're in a little bit higher math class, okay? So, let's amp it up. If you put $5,000 in a savings account and you're earning 12% interest, and when this compounded annually means basically how often you calculate, like you do the math to figure out how much it's actually going to be. Annually means we're going to do it once every year. How much would you have in a year? I'm going to take the 5,000. That 12% gets added on to the 1, so we're doing 1 plus 12%, turn it to a decimal, so that's where the 0.12 comes from. And then raised to this 1 here is because it's 1 year. You can figure out, all right, $5,600, right? You could have just taken 12% of the 5,000 and then just added that on, same sort of deal, but we're going to basically stretch this pattern a little further, okay? We're going to basically modify it by this idea of a compounding period. So we've still got the same sort of setup, but I'm going to change this word right here instead of compounded annually into different times. The way that this equation is going to change then, we still have our initial amount. I'm still going to do 1 plus because we're basically, it's interest in this case, which is always going to be a growing sort of thing. I'm going to take my divide it by whatever that compounding period is, okay? So you're going to see this rate divided by this value n here. T, it's going to be a little tricky depending on how you want to look at that. Sometimes you'll see NT up here. When I say it's based off of the compounding period, we're going to get to some examples with this, but as soon as I turn this into like months, this is measured now in months basically, okay? So let's actually try it. What would it look like if we took the same context, 5,000, 12% interest, but now we calculate every month? How much would that sort of be in a year? Remember, before, it was 5,600 by the end. We're still going to keep our 5,000. This 0.01 comes from literally doing a, let me see if I can't write it here, a 0.12, the 12%, divided by how often I calculate it, 12 months in a year. That's where this 0.01 right here is coming from. Now, since I say 1 year, that would be 12 months. If I only put a 1 right where that 12 is, that would imply how much you would have after 1 month. So basically, to figure out the year, but doing 12 months, I divide the percent over the 12 months and figure out how long or how much it's worth after those 12. It used to be $5,600. Got an extra $34.13 just by changing how often you calculate the interest owed. Excuse me. We're going to try it now with daily. So think how many sort of days are going to be in a year, what that sort of setup is going to look like. Doesn't stay as the same. This number right here, you can take a 0.12, divide it by 365, that's 3. That's where this piece right here comes from. We're adding that number on to 1. Why is it a 365 right here? Well, we're asking for 1 year. You guess that it's going to be higher than 5,600, higher than the last one, lower? What do you think? A little bit more. Our last one was like 56.34. I forget the change there, but an extra sort of $3. Again, if you're able to put this 5,000 in there and just let it sit. Also, if you have an account that's earning 12% interest, reach out to me like right now. That is incredible. You're not really going to see that too often. But we're just playing with nice, pretty numbers for right now, okay? Let's go. Oops. Oh, no, it jumped around. Goodness. All right. Come on, computer. I have my own challenges. I want to basically deal with what would this look like if I compounded continuously? Meaning, right, I could go to daily, I could go to every second and figure out like how many seconds are in a year. But what's smaller than that? This idea is how literal interest works for basically anything that you do, either accounts that you have, or if you were to borrow someone, they're going to charge interest compounded continuously. We saw this sort of pattern a little bit, and we're going to explore that a little bit further, okay? I want to head back here to this guy, give you questions around this, asking you to just set some stuff up and calculate, especially this idea of like a year. You're going to take your rate, divide it by that compounding period, and then based on like if I said 2 years and I'm doing months, this is going to be 24. You're going to do a little bit of math for that. We're going to have some practice, okay? So let's keep going. Oh yeah, a little more Sesame Street, bring it back. Again, the idea of infinite, if count is counting forever. Little bit of sort of hints at some calculus stuff here. For those of you watching live, we're not going to have quite the same time as anyone else watching later. But pause, take a moment here to actually pause and kind of come back and fill some of these sort of things out, right? If you can handle these sort of guys, we're going to give you some stuff kind of like this on your quiz this Friday. Yeah, if I gave you 10% compounded monthly, how much is it going to be after 1 year? Like, can you figure out the amount and sort of the setup for all of these? Number 2 is the same deal. 5.6, bit of help here. 5.6, if I move my decimal 2 places, it's going to turn into this number. People freak out with these things after this place right here. There you go. Just add that guy onto 1. Here's what your equations are going to look like. And again, I'm trying to showcase this 0.1 divided by 12. You can clean all this up, raise it to the 12th power. Why? Well, I asked for 1 year. So that's going to be, in this case, 12 months. If I'm now doing weekly, I think I'm doing that 104. You got 52 weeks in a year. Double that because it's 2 years. This is how you got to be, be careful about that compounding. Here's the answers. Hopefully it came out with those. We're going to throw something like that at you on a quiz. Give you this height of a ball here. We're losing 1/3. Think about how much of the bounce we're keeping, right? We're basically losing 1/3 of the height. We're keeping 2/3. There's sort of your initial value. We keep 2/3. We do it 5 times. Hey, how high is it bounce, right? After 5 bounces, it's down to 65 feet. Let's take this idea a little bit further, all right? I was going to give you some stuff from the book if we'd been able to meet in person, but unfortunately that's not the case. So the idea here is we're going to basically mess with this sort of prompt. Okay, we've got annual interest rate. We've got a $1,000 balance, and this is now basically like a credit card. So if you got a credit card, they might have start you off with 1,000 balance, which is saying, hey, you can borrow up to $1,000. We're going to charge you this 18% annual interest rate. What's it going to look like if you just paying that back, and how quickly this stuff starts to get out of control? Okay. We're asking for how much would it be after 1 week, after 2, after 52 weeks, which would be a full year. How would you basically write the formula? Ideally, we've already got that. Sorry, the little dog here is chewing on some toys. My apologies. And then this idea of effective annual interest rate. They're going to advertise this, and this is something that you will see in the real world plenty, where they're going to be like 18%. By the time the actual math is done, that's not really what it comes out to. So we're going to work through some of that stuff, okay? So that first one, all right, we're the base equation right here. It's 1,000, is what we started with. 1 plus, we took the 18%, since we're doing it weekly, divided by 52. And if I change this right here to 1, 2, or 52, that's where I'm getting these numbers. Right, so if you spent the full 1,000, after 1 week, you already owe them another $350 just for having borrowed that money. That's in addition to the extra 1,000. Right, if you waited a full year, you end up owing an extra, on top of the 1,000 that you borrow, because it isn't free, they're charging you $196.85. So what I'm doing right here, this last part, where it was asking that effective interest rate, taking my 52 weeks, which is this amount right here, or how much, if I spent the full 1,000 and didn't pay anything back, when this amount here, divided by the 1,000, right, which is basically if I didn't at 0 weeks, how much it is, you get this sort of ratio here, which turns out that 18% actually turns into 19.685. That's because we're compounding every month. We're seeing how much you every week. It's a way that basically like sort of jumps how much you owe. The converse is for accounts that you open, they want to continuously compound it as well. More compounding period. A smaller one means they're calculating it more often, so overall it's going to inflate that number up. Be careful, especially with credit cards. If we were to do that same sort of math here, advertising an 18%, and we compounded it annually, that would be 18%. We just saw the weekly math right here, right? And you could go back and we could see this quarterly math. You could repeat the same process, except you're dividing the 18% by 4 for quarters or 12 for months and repeating that process. Ideally, we see what's happening. As we compound more and more and more frequently, this amount is starting to go up. If you were to do a daily compounding, you get to 19.716. So our goal is, if we were to do compounded, which is actually how this stuff works, what's that number going to come out to be? It's not infinite, it's not unbounded, but I mean, right? We're almost an extra 2% more than they average, which if you owe somebody something and every time you're paying another 2%, that starts to add up. I don't know if you're hearing the little one in the background there. So we're going to mess with this sort of idea right here, okay? If you've got a calculator and you're kind of working your way through, try some of this, okay? We're going to take this thing right here, which basically means a $1 credit card balance, just because it's going to be easier to see some of these numbers. And I promise this is all coming back to that letter E, trust me. Being charged 100% interest rate, okay, is what we're going to work with. Why does this make sense in there? Well, the $1 would be this coefficient right here. The 1 right there in front. 100%, if you turned it into a decimal, would be the number 1, which is this guy right here. So what we're going to do is I'm going to ask you to, if you've got a calculator, and if not, you can kind of just walk along and I'll drag the answers over here and see. If you put a 1 into these values, you can kind of start to see what's going to happen with these, right? 1 over n is going to turn into half. So the inside here is going to be 1.5, right? Because I'm doing 1 plus that half. I'm sorry. This is 1 over 1, so that ends up being a 2. My apologies. Raised to the first power. So that number you can figure out pretty easily is going to be a 2. If I put a 3 in here, this is now 1 plus a third. If I put a 5, 1 plus a fifth. If I put a 10, 1 plus 1/10. This number on the inside is getting smaller and it's approaching 1, right? If I put 100,000 in for here, meaning I compounded like 100,000 times in a year. Oh my goodness. Kona, hey, guys, come here, shut up. No. Okay, we're gonna throw out a few dog treats and get them to quiet down a little bit. Everybody has sort of things to deal with from all this remote learning stuff. Okay. As I put larger numbers in, this inside parenthesis smaller and smaller and smaller. My exponent is getting bigger and bigger and bigger. So they end up doing this like between a rock and a hard place thing. And here's what the numbers actually start. If I drag this over here, a 1 came out to 2, and then you could start playing with these other things, and they start kind of like, well, we see this 2.7 thing start to, and then we notice these other decimal places, they're not extending as far anymore, right? The 718 is not really changing. If you've got a calculator, take out e to the x, and I should be able to do this on here. Let's see if I can pull it up. Oh. Sorry about that. This gives you a nice second here to do it. Trying to pull up the calculator on my computer as well. See what that number comes out to be. Come on. Okay, here we go. There should be a calculator you got now. If I do E, it might be a little hard to find. I'm going to go and clear this all out. I'm going to hit the second button so I get the arrow, and then it's this guy right here. You see in blue, or maybe yours is in yellow. You get that piece there. I'm going to type e to the 1 and hit enter. What do we see? 2.718, 2, and then these other numbers start trailing off from there, right? You can imagine that this 7 ends up getting bumped up to an 8. This is where this number, e, comes from. It comes from this pattern right here, this idea of continuously sort of compounding, right? We're doing this again and again and again and again and again and again, of a dollar at sort of 100%, okay? You might still be wondering at this point, like, how far in are we? Great, who cares? What do I need to know for sort of Friday, okay? This is where this stuff comes from. I think this is a cool thing to do. It's worth, again, I've explained, I'm a big advocate of knowing why rather than just do it to do it. If we take this guy right here, as we saw, for large values of n, as we did more and more and more, that we went from 1 all the way up to 100,000, we start to approach this, again, I'm going to say number e here, because it's a letter that we use to represent this number. Kind of like how pi, it's actually a Greek letter that represents a number with this infinite decimal. Come here. Come here. You guys, can we just calm down? Just chill. It's nice being home with the dogs, but then sometimes, too, their timing is less than great. Okay. What are we basically doing to sort of follow along these steps here? And you're going to see where we're linking all this back together. This idea is where the number e comes from, okay? If I were to take this formula and basically divide that n by some value r, well, as long as this piece right here, this n gets changed to an n over r for both cases, great. From step 1 to 2, I'm basically taking a reciprocal right here. That gets me an r over n case, right? This exponent still ends up being the same sort of idea. From step 2 to 3, we see that this r right here disappears and there ends up being 1 on there. What I'm really doing is raising both sides to the r, and then if I raise both sides to the t power, I end up getting this, oh my goodness, left side, which should look pretty darn familiar, right? This is basically that equation from earlier. Come here. What do you think? Lay down. Lay down. Kindly stop. This is the downside of doing some of this stuff live. Is that I guess everyone's going to get to experience this later. This is basically that equation from earlier, right? You might have a number that goes out in front. We took our rate divided by the compounding period, and then this nt is your idea of kind of how to figure out sort of years from some of that. Well, it ends up matching, and it can be simplified down to e to the rt. That ends up being very helpful and gets used for a whole lot of calculations for this stuff in the future, okay? Oh my goodness. I'm going to have to accelerate some of this a little bit. Showcasing right here, $2,000, 13% annual interest. If you were to go back and repeat those same steps, if you compounded yearly, monthly, daily, every second, what this amount comes out to be, a 13% interest rate, you can see it start to just shift and inflate just ever so a little bit. If we were to instead replace this with e to that 0.13, and we're leaving t as 1 because we're doing 1 year, take a 2,000, type that number. What are we going to get? Guys, you got to shut up right now. I'm going to do 2,000 times e to the, oops, let's try that again. Oh my God. If I raise it to 0.13, what number do we get? 2,277. Well, you might notice it's pretty darn close to this, to a point where that rounding, that last place, that tenths place, your cents is never really going to change, but that's where it's coming from. This is why we like it. This is where it comes from. It's not just like made up. It's from some actual patterns here. Oh my God, guys. Stop. No, I'm streaming. I think that's pretty exciting stuff. We had a bunch of gifts and Bill and Ted's for you. Anyhow, okay. At this point, you've kind of seen where e's coming from. It is just a number, and it's the base of an exponential expression, right? This idea here, this is no different than like 2 to the RT, except it's going to allow us to shortcut a lot of these properties with some of the ideas of like interest and how these things are calculated. This is how it actually is done in the real world. This idea of ln is going to be a logarithm for base e. Everything we know about properties of exponents and properties of logs is still true with all these things, okay? Let's say I gave you both of these things and asked you to sort of solve for these, okay? And you might be wondering why we're saying ln, where that comes from. Sorry, I'll rewind a little bit. ln for natural log, it's from the French like logarithmic natural. I don't speak French. French mathematicians were massively critically important for a whole lot of stuff going forward. So they basically figured that this piece right here was pretty handy. This is something that's going to come, it's worth locking into your brain, okay? If I gave you this, right, on its own, we know that's equal to, oops, didn't do that right. Right, if we see log on its own, that's the same as a log base 10. If you see something like this, a log base e is the same thing as a natural log. Okay, stop. They're the exact same thing. Everything you know about logs is going to work just fine. The advantage is, right, like, so if I took this 10 to the x here, oh my God. Okay. Come here. Come on. All right, let's just come up here. Okay. All right, we got a guest on the stream, everybody. Here's Obi, because these guys are going a little wild, so my apologies due for a moment. Obi, look at the camera, bud. All right? Okay. All right, if I took 10 to the x, which is equal to 32, and asked you to solve for this, right now, most of you would probably do something like, okay. Take a log of both sides, right? Do this. I could do log, come on. Then we go about our way, you bring the x down in front, great. And then you start dividing over. The reason this works is a log base 10 and a base 10 undo each other, right? Those are going to cross cancel, which is going to give me just x equals whatever the log of 32 is, okay? Excuse me. Guys, you gotta stop it. Okay. You can figure that out. Type in your calculator, you get a number, right? 10 to what power equals 32? Well, it's, I don't know, it's going to give you some sort of number between 1 and 2. Figure it out. If you were to take this guy, this 4 to the x here, and repeat that same sort of process, I'm going to do it, but instead of a log base 10, which you could do this. Yeah, this is the downside to some of the remote pieces here. You could do that. What I would instead probably choose to do, though, is a log base 4, because it's going to undo that base 4, right? That's how I was sort of taught I like to think. You can do it that top way. It totally works. You can do it all with base 10s. I like this because it's going to cancel these things out. Hello, Otis. I was posting in on the Math 2 stuff. We'll have some stuff for you guys soon, though. What's this going to give me? Right? And we know how to do this. You can do change of base formula. You can type this into sort of your calculator. You can do log 32 divided by log 4. Great. All that's fine. It works. I like to do it with the log base 4. Sure. Let's come over here now. If I have e to the x is 32, what's going to undo this? Well, if I repeated the same process, I could take a log of both sides. Okay, it's going to look like this. But generally what you're going to see instead is rather than take a log base 10, we want to undo the base. I'm going to do a log base e. The idea is log base e and base e cancel out, and you got to figure out what log base e of 32 is. Well, what is that really going to look like? No one's going to write log base e. What you're going to see instead of this, what did we say log base e was? We've got double copy down here, the natural log. If I were to do this instead, the natural log is going to undo a base e. So I'm just going to get x equals ln of 32. You'll typically hear it called ln rather than full natural log. You might be wondering, well, how the heck do I do that? Go back to the calculator. You might remember from previous weeks where I mentioned things that your calculator really only knows two bases, 10 and e. I could do log of 32 right here. Right? That's what we needed for that previous question, right? If I did 10 to that power, if I did 10 to that like 1.5, whatever sort of craziness thing, what do we get? Hey, 32. To do a natural log, it's right here below. And you notice that also we see a log with a 10 to the x because they're inverses. What do we see with natural log and e to the x? They're inverses. You want to type ln of 32. There you go. Now, it's asking the question, e to what power equals 32? It's not a pretty number, and that's fine. But the process is still the same. Everything that you know about logs is still going to work. And tomorrow we're going to have another video that's going to kind of cover some of the, just if I gave you a problem and it was regular logs, how would you do it? Great. What changes with natural log? Nothing. Nothing's really going to change. It's just a specialized log base for the number e. I think that's all I got for you right now. Yep. Okay. So tune in tomorrow, or whenever sort of you like. There's going to be another video that's going to showcase, again, some of the same sort of stuff that you did last week. Everything that you know is still true. We're just going to change things to E and LN just to get a little more familiar with that. This week's assignment is going to be a quizzes. It's already posted because there wasn't a ton in sort of the book stuff that we could really kind of pull from. Feel free to go through and work through that. You can do it multiple times if you'd like. Please use your first and last name. If you want to go ahead and give it a try, great. Go ahead and give it a try right now. You might be pretty darn successful at it. And we've, in a way, covered everything that you need. We'll give you a little bit more practice and nuance with that sort of stuff. Probably upload some additional practice pieces if you so choose to do. The only required assignment for this week is that quizzes. We'll have another sort of regular legacy quiz on Friday. Feel free to stop into office hours. I encourage you if you got questions or even just to say hi and let me know what you're doing. Hope you're staying safe, staying healthy, trying to figure out some way to combat some of these things. If you got any great ideas for things to do at home under self-quarantine, please reach out. I hope you're safe and well, and we'll see you all in the future.